Well, I am trying to teach, but we don't teach enough. Here I have paper. That you don't need to give an answer with a high precision, because you just need to give an idea of the order of things. If you need more detail, you can have a computer to calculate. You don't need to use your hands or your mind to do everything. But just to fix idea, what is the question is how many times? So how many seconds you have in a day? Do you know that?
Yes, it's 86,400.
This is yeah, perfect. That is the number that is good to know. But if you look like very far away without the glasses and you kind of put your eyes small and you don't see the details, 86,000 is like 100,000. Okay, it is similar to it. It is the same order of magnitude. It is the same order of magnitude. It is more closer to is more closer to 10,000 than to 100,000. No, it's between 10,000 to 100,000 is closer to 100,000. So I will say 10 to one day is something like 10 to the power of 5 seconds. That will be my first. That is one day, 10 to the power of 5. Okay?
Actually, it's not okay because there's like 14,000 seconds difference.
Yeah, but it's in the order of, we will be off by, I don't know, yeah, 15% of error, 15% of error, if you like. But it's the order of, it's not twice, it's not half, it's not 10 times more. It's in the order of. And we'll give you a good way to think about it, because remember that here we are simplifying many, many things, so you get an idea. So essentially, the number of days is the number of seconds, and you take -5. So instead of, okay, you get the formula for days, something like 10 to the power of 3n minus, you should have a way to write this in the screen, no? 10 to the power of 3n minus 11. I will write a formula like this. Can you see? A formula like this for the
number. We can stop the share so we can look closer to your paper.
Good idea. Good idea. I didn't think about that. You see, the people are smart. They should just do it more often. There.
Not this way. When you started the lecture, your camera was all screen, but now it's small as ours.
I guess because you other people are speaking. Maybe, I don't know. Because
there is a gallery view and speaker view in top right.
Yeah.
I can see full screen of you.
Oh, okay, view. Okay. It was about me. Sorry.
No. I mean, we are all learning. Don't be sorry. Like we are all learning. I don't know. I mean, come on. We are all learning here. So I'm saying something like this. No, here. I should have the other camera. In fact, I have a better camera. The cell phone. Or maybe I can write somewhere in the screen. There is something like I can draw in the. I don't know. Do we have a better tool? Yes, we have a better tool. Thank you for reminding me that I have. Okay, but but essentially we are thinking. So what were the numbers? Let me go back in the slide 1 second. Sharing. Okay, I'm sharing again just to see the numbers. What is this zoom thing? Okay, zoom is confusing me. Share screen here. Sharing this one. Just a second, okay? And I think I can use there is a drawing tool here somewhere. Annotate here. So what I'm saying is that this is essentially 1 second. Oh my gosh. Undo. 1 second is super hard to write with the mouse. It is even harder without the mouse, but anyway. And so this is the second, this is like 10 days. Okay, if you want to be more precise, maybe it's 8 days, maybe it's 12 days. I don't know, but it's not 1 month, 10 days.
So are we rolling the days in tens or hundreds or something?
Yeah, you can do something like that. So for example, how many seconds you have in a year? Well, a year is something like 300 days, 300, 350. So you can do it more finally, but I will say something like 10 to the power of 7, with a factor of 3 or something. To but something in the order of 10 to the power of 7. No? It's 10 to the power of 7, 10 to the power of 8. Yeah, let's say 10 to the power of 8, just to fix idea. Therefore, this is many years. This is something like 10 to the power of 10 years. Something like that. Sorry about my calligraphy, but I have bad calligraphy even without the mouse. Fine. You follow my logic here?
No,
Yes.
after the second I got lost.
Okay, let's use the pen and paper thing.
No, it's not about your calligraphy. I don't.
No. No, I'm saying just to reason. What I'm doing is this. I am trying to do kind of scientific notation, and then I am being lazy. That is the bottom line of this. So you didn't like very much when I put the iPhone vertically. Do you like when I put the iPhone vertically, or yes or no?
Yes.
Okay, good. Someone said something. Good. Matt is the one that knows because he has seen my iPhone. Okay, I hope the computer doesn't melt with this thing, but let's see. Let's see. This iPhone. And the trick is I want to send you, I can send this video later. Okay, I have video here and I can put it somehow like here. Somehow, I'm putting it here. We will see, okay? Experimental method. We are on learning. Fine. This exercise beyond bioinformatics is a way of reasoning. This is important because essentially the question that you have to ask you every time you do an experiment, but in particular when you're using computer is, can I do this in a reasonable time? Do we have time for doing this? So I'm sharing the screen again.
By the way, may I ask what are we gonna do with the quiz? Should I send it or?
Yeah, of course. But you want to do it later? Yeah, let's do it.
If we're gonna go back, I can just wait.
Yeah, just wait. I mean, okay. I need to stop. I will save this. No, I will stop. How I stop the drawer here? Click now. We need to talk about this. Okay. The goal of the quiz is double, no? For one side, can you see what are you seeing here? You are not seeing my...
We're seeing your beautiful calligraphy.
That is not good. I wanted to share my iPhone here. Okay, share. Okay, connected, trust, open. Oh, come on. Okay. Okay. No, not that one. This is a funny thing. Okay, camera. Okay, and you want to oh, too much sideways. You see yourself there. Okay, fine. Yes, no?
Yes.
Yes.
A little bit to the left, maybe.
Yeah. I was my hand there. And I am recording this thing, so I will send you the video later. Okay. So what was the reasoning this? So here, here, like this one. So here. Okay, good. One day is 86,400 seconds, which is 8 times 10 to the power of 5, no? No? 3, 4, to the power of, 8 to the power of 4. Which is, if you are a little more, how can I say, open-minded, is 10 to the power of 5, just to simplify the computing. Therefore, when we say that we have 10 3n minus 6 seconds, is the same of saying 10 to the power of 3n minus 11 days. And that means essentially that if we have 4 sequences, means that we take 10 to the 12 minus 11 days, something like, it's not exact, you have to do it, but it will give you an idea of how much you have to wait, 10 days. So you need to, if you are going to do this with this method, you need 10 days of computing. Now, following the same logic, if we have 8 sequences, 8 sequences will be 10 to the power of 24, 3 times 8, 24, minus 11 days. This is not equal, but 3 to the power of 11 days, which is 10 to the power of 13 days. And the question is, how much is this? Well, there is a point that I give you a hint. P seconds is equivalent to 10 to the minus 9 and 1 nanocentury. And this is a shortcut. P seconds is a nanocentury. In other words, in a century, there are 10, let's write it in a different way. A century is something like 3 times 10 to the power of 9 seconds. And here we have, and you divide, if you divide by 300, if you divide by 300, you
I
will
don't
have...
understand where the 3 came from. 1 century equals 2?
No, the shortcut is this. If you are, the shortcut is you take the number p.
Oh, okay.
And I approximated p by 3. And if you divide by 350, 365, you get something like 10 to the power of 7 seconds in 1 century. So, not seconds, days. 1 century is p times 10 to the power of 9 seconds. 1 century, therefore, is something like 10 to the power of 7 days. And with 8 sequences, you have 10 to the power of 13 days. In other words, 8 sequences. Let's draw one, I said 8. 8 sequences require something like 10 to the power of, what is this? 6 days. No, centuries.
No,
1 million.
Million centuries? Oh.
no, it will be like 2 centuries,
Where I am wrong?
approximately. 1 century is equal to 10 times 7, and we got
Days.
10 times 13. Okay,
Yeah.
and
So
it will be like close to the 10 centuries.
no, because you essentially.
Okay.
Okay, yeah, no. Let's do one step. We say going back here. We say 8 sequences. We say that they need 10 to 13 days. That is equal to 10 to 13 divided by 10 to 7 centuries. And that is when you simplify and you get what we say here, 10 to 6 centuries. Okay?
Okay, I got the math wrong.
Yeah. That is the second. So the point is, before even going to the computer, even before you open the calculator, the idea is to think about what is the size of the thing. I mean, the calculator, it is easy that you make a mistake. I mean, if you do the calculation wrong. So this exercise with powers of 10, nothing more than powers of 10, allow you to check quickly what are we talking about, what are the orders. So you realize if this is 1 million century, I don't care if we are wrong by 20%. Maybe I am pessimistic and it takes 20% less time. I give you 50% less time. It is still 500,000 centuries. So I don't care very much about the decimals because the big numbers are so big that they don't care. So, and just
like
to fix
heuristic.
Sorry, say again?
It's like heuristic, right?
Exactly. That is exactly. This is a heuristic to calculate the thing. So that's you get an extra point. You go the correct idea. So do you remember the last one? It was 12 sequences, 10 to the power of 30. Well, how many seconds is 10 to the power of 30? Let's stop this thing. I will send this video later, okay? We share the... okay, let's do something. I will talk here. You fill the quiz. The reason of the quiz is one, attendance, and second, to trigger this discussion, okay? So I'm going to do this. We talk now 2 more minutes to fix the ideas, and then you fill it just to have the attendance, okay? But this is the exponential. This is 1 second. This is 10 days. This is 1 million centuries. And how much is 10 to 30 seconds? Well, let me tell you this. The age of the universe is something like 10 to 21, 10 to 24 seconds. In other words, if we starting doing this with the Big Bang, we still don't finish. We need like 1 million universes to solve 12 sequences, all the story of the universe. So that is why my question were like this one. What is the largest multiple alignment that you can do in your life? So the question, how long will you live? Tell me, how long will you live?
Approximately 65 years.
Approximately, well, let's say 100 years. Let's be generous. Yeah. It's not 10 years, it's not 1,000 years. It's more like 100. I'm thinking in power of 10. So you can essentially say like, what is the largest number of sequences that can be aligned? Well, that is again a super tricky question because it depends on how much time you have. What happens if the computer are 1,000 times faster? If you super technical advance and the computer or I give you 1 million times faster. So instead of 1 million centuries, you do in 1 century with 8, but you cannot do 9. The biggest point here is the size of the sequence. What happens if the sequences are longer? It is much worse. But if they are shorter, if instead of 1,000, if they are 100, you can do more, but not much more. So, okay, I give you, I don't know, 1 minute, fill it, but and to have the attendance. And in the meantime, I will talk to you. Wake up. Some people need coffee. Yeah, doing exactly to the number of days and years is complicated, but approximately is easy and is good enough for the purpose that we have. You can try what happens if m is 100. And you see that making computer faster will not change the bottom line. And the truth is doing real alignment with 10 sequences is beyond, my point is this, it's not beyond our capacity, it's beyond any capacity. This is the kind of problem that is solved in theory, but not in practice. And it's not solved in practice essentially because even with the highest technology that you can even imagine, I mean, at least the kind of computer we have, maybe quantum computer can do something different, but with this kind of computers, even if we make them 1 million times faster, we still cannot solve in a reasonable time. Okay? Yes, no?
I have a question.
Go ahead.
So the first question, I got the math, that's okay. But the error percentage, I mean, if he says 1 million and 20% of the error margin, it's a lot because it's 1 million. With the small numbers, maybe the errors will be smaller, but when numbers get bigger, the errors getting bigger.
Yeah, of course, it's but they get the same percentage of error.
Are we caring about the cost here?
Yeah, I mean, we are caring about the time, which depends on the cost and the technology. But the bottom line is that even if you care about the cost and the time, even if you, I mean, the basic point is that if we are talking about millions of years, that 20% of error is still too much. Even if you say that 20% is still too much. Now, if you want, you can do it again with more decimals. I make a very quick thing. The idea is this. The first thing that you do is to make an approximation with powers of 10. Powers on 10s are easy to think. It's 1 million, 10 million, something like that. And you get an idea. We are talking about millions of centuries. Now, if you want to make more precise, you do it again with the calculator and you will get something more precise, but you know it as something in the order of millions of centuries. It's not 10 days, it's not 11 days. Now, if you get outside the range of 10, I mean, when we say 1 million centuries, it's something between 10% of that and 1,000% of that. And it's something between 100,000 centuries and 10 million centuries. It's a big range. But to give you an idea, what are we talking about? It's 10 to the power of between 10 to the power of 5 centuries and 10 to the power of 7 centuries. That is the range that we are talking. It's a big range, but there are many things outside. Most of the things are outside. Okay.
And with the second question, do we have to write like if it's 1,000, should we say it's 10 times 3? Do we have to say that?
You can write whatever you find that is a reasonable explanation. That is the second part of the exercise. What you want to say, how you want to say it. So, for example, a first reasoning will be like if m increases, this increases, if m reduces. That is kind of the easy one. But essentially, my reasoning was this: if instead of 1,000, m was 100, shorter, then the formula, instead of 3 to the power of 10 to the power of 3n will be, let's quickly, will be 10 to the power of 2n minus 6. If I had the shorter sequences, and then you can do the analysis with this 2n and kind of quickly see how many centuries, how many universe life, or something like that. The bottom line is this: if you have shorter sequences, you can align more sequences, and that you would like to know what is that trade-off. Like you can do 4, maybe 5 sequences of size 1,000, but maybe you cannot do if they are shorter, maybe you can do 10. But certainly, I think everybody should see clear that we cannot align 1,000 sequences or even 100 sequences. Okay? And unfortunately, that is what we want to do. So what shall we do instead? Okay, last minute. We can finish the quiz, finish it. I have 8 answers and I have 2 people that are not answered yet. No. I have 12 people in the class and I have 4 people have not answered. Well, 3 people. Okay. Please answer because this I will take the attendance from here. Okay. And I will check attendance after the class. I will check the attendance and I will update the what is the name, the calendar, the web page, the Google Sheet, and then you complain if I didn't put you. Okay. Yeah, because I need to do it a little more carefully. Okay. The point of this exercise is to make you think and about the size of things, the order of magnitude of things. This calculating is called thinking in order of magnitude, in powers of 10, if you like. That is a very basic thing that it is easy to do and it should be good to know. I don't know. We have an exercise like. What is the size of the building of the department, our department? What is the size? How many cubic meters you have there? How much people can you fit inside the building? What is the weight of the building? I don't know how much time you need to use to grow. If you are working with a culture, how much time you need to grow that culture? How much? And in this case, how much computer time you need to do something? Please notice that it is not that the computer cannot solve the problem. It is not a physical limit. It's just that we die before the computer finish. It's a biological limit, if you like. It is a good practice to be thinking about what are we talking about, what is the order of magnitude. When people say like there are millions of people dying of COVID, or there nobody is dying of COVID. Well, what is the order of magnitude? What are we talking about? Okay, and the last question that we have here: what can we do to align more sequences? Okay, people are moving their lips without using the microphone. What can we do?
Basically, we need maybe to build faster computers, because in the formula there's
yeah, well, this is the question number 3 is, what if we make faster computers? If we make faster computer, instead of 1 million centuries, you will take 1,000 centuries. Good. It is much faster, but it is still thousands of centuries.
And the other option maybe to intervene with the sequence, maybe not.
Yeah.
I don't know. I'm thinking about the formula. There's the sequence length and there's the computer.
Well, Arda should speak now. It is your chance to say. What do we do if we cannot solve a hard problem? Think about...
simplify, but how?
Yeah, well, you have a magic word. Say the magic word.
Heuristic?
Heuristic. We need an heuristic. Remember that if you cannot find the keys in the place that you lost them, you look for them where there is light. You solve the easy problem that hopefully is not very different from the hard one. So, heuristic. Fine? As you see my screen, no?
We see the slides.
Heuristic. Yeah. So that is what the trade-off of life. The trade-off of life, that this kind of problems are intrinsically hard and cannot be solved with this kind of computer. I mean, people dream that if you have quantum computers that are capable of kind of doing all the options in parallel in the parallel universe, essentially quantum computer is like having computers in the parallel universe. And you have infinite parallel universe, or you have infinite computer running at the same time, and they somehow collapse and give you, well, something like that. But we cannot do that right now. With the current kind of computer that we have, we need to do a simplification that is an heuristic. And the most common is what we call progressive alignment. Okay, maybe I should say something also more general here. Every time that you have this kind of problem, and you have this kind of trade-off that you have to sacrifice speed in the name of accuracy. You get something that is not a perfect result, but is fast. Every time you have this kind of trade-off, you will have many people giving you many answers. For example, in the case of BLAST, BLAST is the most common, but it's certainly not the only tool that people use to solve the looking in databases. It is just the most popular. Same with Google. Most of us, we use Google, but Google is not the only search tool, and they give you different results. Well, in the case of multiple alignment, there are many versions, many heuristics. Many programs that trying to do different heuristics, they essentially make different assumptions and they make different things. So, and the many. So part of the confusion is that different people will use different tools and different tools will give you maybe different results. If all the tools give you the same result, you are kind of happy. But okay, I will speak about kind of the most common. I think it's the one that people understand. To fix idea, in fact, I'm speaking about the one that is kind of the one that people, the first good one. The first good one. There are many newer that are more complicated, but let's start with the simple one. So the idea is called the progressive alignment, and I can give you the name of the guy that is called by Feng and Doolittle. I will give you a link to some paper. There's a paper that a review of these things. But essentially, what they say is this: okay, we know how to align two sequences. That problem is solved. This is for global alignment, so you do the global alignment of the thing. We know, and then when you have them, you add a new one, and you somehow try to put the gaps. Comparing with these two, you need to find a score of aligning three things, and then you put a number 4 and number 5. So this is the basic idea. You start with 2 and you add one by one until you get a bigger one. Then, well, what I was saying, there are many approximated solutions. There are many different heuristics. I will give you some names in the next slide. And the main difference is how you sort them. If you are going to align one by one, you start with 2. What are the first 2? Let's say that you have 100 sequences. How you choose the first 2 to align, and how you choose the next one, and how you choose the order. There are different approaches for that. There is a second question that if you align it 2 things and you get a new sequence, will you look back and change the original alignment or just keep it? Like if you make an initial alignment, will you change your mind later or not? In the simple case, you don't change your mind. I mean, you align the first two and that is solid and you never change it back. The most advanced, they kind of change their mind and they go back, and that, of course, take more time. Do you have any additional information? For example, in the case of proteins, some cases you know that the protein have some 3D structure and you want to use that thing, like the part that have the same 3D structure should be aligned. You can just force things to be aligned. And then the last question that is important here is how to find this formula. Because we have these PAM and Blossom matrices for 2 amino acids, but we don't have a matrix for 3 amino acids or 4 amino acids or 20 amino acids. How we calculate this score? These are the kind of questions that different people got different answers, and so that is why we have different programs. And the one that I got here are this. Clustal, the one that I'm going to talk today, was, if not the first famous, the first that people use a lot. And it's kind of the easiest to understand. In my time, the program were called Clustal W and Clustal X, and now there's Clustal Omega. You have to see them. Then there is the one that people really recommend, is T-Coffee. And they have an extension called 3D Coffee, that is the one that can work with 3-dimensional structures. And there are 2 ones that I also see a lot of people using, Muscle, and MAFFT. Okay. There are many differences, and to be honest, you have to go and read the manual if you want to know the difference. Probably the point is that if you have a sequence, the set of sequences that you want to align, you should try to align them with more than one tool. and see if the different tools give you more or less the same result. Because if they give you very different results, you know that you are in trouble. All these sequences work very well when the sequences are very similar. I mean, if the sequences are identical, there is not too much to think. They are all the same. If they are very similar and 0.1% of mismatch, they will work again well. They get complicated when the sequences are more divergent, when you try to align, I don't know, a gene in human with a gene in Pombe. Then they start to be problematic.